Hi, this is a video on the stability of linear systems. What is stability? So we have convergent and divergent systems. As you can see in the black line here, a stable system is one that will converge to a solution. In contrast, a divergent system, seen in green here, is one that increases exponentially over time and does not come to a steady value. So a stable system, when it is perturbed, will still return to a steady state. You can perturb the inputs or the state variables. In contrast, when you perturb an unstable system, it will not return to a steady value. So more on perturbing the system and determining the response. There's two types of stability. Internal stability is the ability of the system to return to steady state after one or more of the state variables have been perturbed. Our state variables are like x1 or x2, and they're part of our system. So when these are perturbed, the system will still return back to its original steady state value if it is a stable system. Alternatively, external stability is the ability of the system to return to a new steady state after the input has been perturbed. The input is the initial condition given to the system. If this is changed and the system is stable, the system will still return to a steady state value, but it will be a different value because the concentrations of your state variables x1 and x2 will have changed. This external stability is also referred to as bounded input, bounded output stability. So phase space. I'll be showing you some phase plots in my software later. So in general, a phase space is all the possible states of a system shown in a graph. And we show this by varying the initial conditions and showing the response of the system. Each axis represents a state variable, so in our case it will be x1 and x2, and it illustrates a variety of transient responses around steady state. So there are a few different ways to determine stability. In one way, you want to find the eigenvalues of the system. So you do this by first identifying the Jacobian matrix. As you can see here, we have the two differential equations that define our system. You can expand this to have as many differential equations as you want, but we're doing a two-equation system. So here you can isolate your A, B, C, and D values that form the Jacobian matrix. You then calculate the eigenvalues of the Jacobian by finding the determinant. If the eigenvalues are negative, the system is considered stable, while if they're positive, the system is considered unstable. And this is because when you find the solution to the system, the eigenvalues end up being the powers in the exponential. So if they're negative, the system will return back to a zero or steady state value if it's perturbed, while if it's positive, it will continue to exponentially increase. Another way to determine stability is to identify the transfer function. In the denominator of the transfer function is a characteristic equation, and this has the poles of the system. Similar to the eigenvalues, if the poles are negative, it's a stable system because they're the solution and they're the powers in that solution. And if they're positive, the system is unstable. So there are 6 different systems I'll be showing in my software, and they just define the stability of the system. So moving into the software. So this is the software that will plot this and show you the stability of the system. So first off, I defined the Jacobian matrix. So I did this by first setting up the array with A, B, C, and D values, which as you can see down here are inputted by the user. And then I use this function to identify the eigenvalues of that matrix. And again, that's just calculating the determinants. So then here I set up the differential equations. I have my differential equation for x1 and my differential equation for dx2 over dt. This command here is just defining my subplots for the system. And so here's the code that defines the phase plot. So first I set a very narrow time range so we can do our phase plot. Then I set up the initial conditions for x1 here and x2 here. And I'm just trying to get a range because the phase plot will show you the range of initial conditions. So here I'm doing this for some specific I and j value. Here I'm solving the system for that specific initial condition. And then I'm plotting x1 and x2 versus each other on the graph. This command here just adds arrows to the phase plot and shows the directionality of the arrows is very important. If they're pointing inward, it'll be convergent. Outward is a divergent system. So here are just the plot parameters for the phase plot where I'm setting the axes and doing the labels. This is setting the overall figure caption for all 3 graphs. So this code here is plotting the concentration versus time. In this instance, I'm setting a time range from 0 to 10, and then doing one initial condition, which is 10, 10 in my case. And that was just arbitrarily chosen. And then here we're solving the system again. And then these are just the plot parameters for the time plot. So we plot x1, x2, both versus time, and then just add labels. So the third plot I'll be showing you is an argand plot of eigenvalues. So we have the eigenvalues that we found earlier, and we identify the real components of these eigenvalues and the imaginary components. Once we isolate these, we're going to plot the real component on one axis and the imaginary on the other. And then down here is just plotting the behavior of the system, and this is done by identifying the eigenvalues and then deciding if the real component and imaginary component, based on whether they're positive or negative or zero, you get these different combinations. Okay, so I'll run you through a few examples of systems with the code. So first off, I'm going to be showing you a stable system, -5, 1, 4, and 2. So I'm just inputting the values of the Jacobian matrix. So as you can see, we result with, these are the eigenvalues. So we have negative, correction, I didn't put in -2 for the D value. So let me try this again. And the reason I know this was an error is because the eigenvalues should both be coming out negative if it is a stable system, while here we had one positive value. Okay, much better. So we can see they're both negative, so it is a stable system. So as we can see, the plot here, so let me walk you through the plot. So on the left, we have our phase plot for x1 and x2. You can see x1 is on the x-axis and x2 is on the y-axis. So we set our axes from -10 to 10, so that's good. It matches what our input was. As you can see, these black lines are all pointing inward, which suggests it is a stable system because they're all coming towards the center line. So regardless of my initial conditions, since it's a stable system, I should get a steady state system. So as you can see here, we plotted 10, 10 as our initial condition for the concentration versus time graph. You can see we get this spike because as we apply the input, but as time goes on, it goes back to a steady state value at 0. And then on the argand diagram, so we had our eigenvalues of -6, which is here, and -1, which is here. So that all worked out well. So I will show you the next system, which is a center system. So for this system, I'll be inputting the values of the Jacobian again, so 3, -9, 4, and -3. So in this scenario, we only have imaginary components of the eigenvalues. There's no real component. So here we have a behavior of the system is a center system. So this system is a little different because you can see it has an oscillation as time goes on. It's still a stable system because, as you can see, the arrows are still pointing inward. So it's still converging, but it takes a much longer time to converge because it goes around and around. So for 10, 10, which is out here, it has to spiral in a lot to get to steady state. So in our time window of 0 to 10, we don't reach a steady state. We just get this oscillation. The eigenvalue diagram shows the eigenvalues that they're imaginary. There's no real component along the x-axis. Okay, I'll now show you a saddle point system. So we have the values 1, 2, 3, 2. So in this case, we have eigenvalues that are only real and they're opposite in sign. So as you can see, it is called a saddle point system because you get this hump of a saddle point. So this system's a little different. You can see the arrows that aren't along the center line point outward, which implies it is not a stable system unless you're along this center line. So our initial condition of 10, 10 is out here, so it's in the unstable region. And as you can see, instead of getting a flat line as time goes on, we're getting an exponential increase in our x1 and x2 values, which implies the system is not stable at this point. And then on the argand diagram, we see the values are all real and we have -1 and 4. Stable system. So next up, I'll show you the unstable system. So 0, 1, -2, 3. So we're getting only real components in the unstable system, and they're both positive, which, as I stated prior, means that it's going to exponentially increase in the solution. So you can see the arrows are pointing outward, again, which shows it is unstable. Even the centerline arrows in this case point outward. So there's no initial condition we could give this system that would make it stable. The graph exponentially increases again, as we would suspect, and the eigenvalues are plotted 1 and 2, and they're both positive. Okay, the last system I'll show you is a spiral sink. So -1, 1, -1, -1. Okay, in this case we have both eigenvalues as negative, and they have real and imaginary components. So in this case, in the spiral sink, our arrows are pointing inward, which is good because it means it's stable. Similar to the center system we saw earlier, we still have a little bit of this oscillation, which comes from all of this circular motion here. So, but in this case, we do reach steady state before our time of 10. And then on the Argand diagram, you can see the lines are slanted. So in this case, we have real and imaginary components. But that is my program. So thank you for watching.